All right, in section 1.6, we're going to talk about a bunch of different types of equations. We've already talked about Bernoulli, and the good news is I think Bernoulli's the hardest. So let's do the next kind. The next kind is homogeneous. Anybody know what the word homogeneous means in math? There are two different definitions. One, it means equal zero. That's not the definition we need here. If you're taking linear algebra, you've used that word homogeneous, and it means equal zero. In chapter 2, we will use the word homogeneous, and that will mean equal zero. In chapter 1, homogeneous means something else.
It doesn't mean one side is equal to the other?
No. All right. Homogeneous first order equations, this means each term has the same power. All right, so let me give you an example. This is problem number 2 out of section 1.6. 2xy, y prime, equals x squared plus 2y squared. All right, so what you should do, you're going to have to start looking at differential equations and figuring out what type they are. They could be separable, they could be linear, they could be Bernoulli, they could be homogeneous. In this case, you should recognize that this one's homogeneous. What's the degree of this term? 2 squared. What's the degree of that term? Squared. What's the degree of this term?
1. Well, squared if you integrate it.
The degree is 2. When you have variables that are mixed, you add the exponents. So that one has degree 1, that one has degree 1. Altogether, that has degree 2 as a term. So when variables are mixed, you add the exponents to find the degree of the term. So these two are easy because they're both x squared and y squared. Those are clearly degree 2. This one, because variables are mixed, you have an x and a y. You add those together, 1 plus 1 is 2. All right, so this equation is homogeneous because each term has the same power.
By together, do you mean in the same term, like 2xy or x plus y?
X plus y, those are two separate terms.
Okay.
So if I had this over on this left-hand side, 2x plus y, y prime equals x squared plus 2y squared, that would not be homogeneous. Because this term would be degree 1, this term would be degree 1, but these over here would both be degree 2.
Okay. So
that equation would not be homogeneous. You'd have to figure something else out with that one.
Okay.
All right? When the x's and y's are multiplied together, you add the exponents. Okay, so I looked at that equation and I did determine that that equation was homogeneous because all the powers were the same. When an equation is homogeneous, you're going to make a substitution. You're going to let y equal vx, where we're thinking of v here as a function. V is not a constant. V is a function.
V of x?
V times x.
Oh, v times x, but v is a separate function.
V is a separate function. So when I take the derivative y prime, on the right-hand side, I have to use the product rule since I'm multiplying two functions together. So y prime is going to be, I leave the first one alone, that's v. I take the derivative of the second one, the derivative of x is 1. Plus, I leave the x alone, and I take the derivative of the first one. What's the derivative of v? V prime, or dv dx if you want to write it that way. V prime. So it's v plus x v prime. So we're going to make those substitutions. Everywhere we see the letter y, we're going to write vx. And everywhere we see the symbol y prime, we're going to write v plus x v prime. So let's do that. We have 2x times vx times v plus x v prime equals x squared plus 2 times vx, quantity squared. Now what? How does that help? Well, what should happen at this point? At the beginning, every term had degree 2. Now that we've made this substitution for y equals vx, every piece should have an x squared in it. Since our original powers were all degree 2. We've got an x squared right there, x squared right there, and x squared right there. How does that help? You can divide the whole equation by x squared. All right, so I'm going to do that. 2v times v plus xv prime equals 1 plus 2v squared. What should now happen? You should be able to do some algebra, and this should become a separable differential equation. So let's do a little algebra here. We're going to distribute 2v squared plus 2xvv prime equals 1 plus 2v squared. Well, something real nice happens there. Subtract 2v squared on both sides, those add up to 0. We have 2xv, and then I'm going to write this as dv dx equals 1. And I do think we can separate our variables. I'm going to write this as 2v dv equals 1 over x dx. So that's the trick behind a homogeneous differential equation. You make the appropriate substitution, do a little algebra, and your equation is separable. Integrate both sides. You integrate the left-hand side, you get v squared equals ln x plus c. Not quite done. No, you don't want to square root both sides. What you really want to do, the equation started with x's and y's, so you should end with x's and y's. So I'm not going to write v squared. Instead of v, I'm going to write y over x. So this becomes y over x squared equals ln x plus c. So I would write my final answer as y squared equals x squared ln x plus c x squared. Because I would keep the absolute value of the x mainly because they did not give us an initial condition. If you didn't put the absolute value on a test, I probably wouldn't mark it wrong. But you never know, because I guess in theory x could be a negative number, and the rest of the equation would work. So I would leave the absolute values there this time. Other questions on that one? What's that? Get rid of the x? Yeah, right here I cross multiplied by the x squared. Give the x squared there. Yeah, it's down near the bottom of the page, a little hard to see. Other questions? Max?
So do we just always replace y with v times x?
When the equation is homogeneous,
Okay.
you will always replace y with vx. And you will always replace y prime with v plus x v prime.
Okay.
And then do the algebra, your equation should be separable.
Okay.
Other questions?
What are we looking at for our first test?
When are we looking at our first test? That's an excellent question.
We have a physics one next Friday.
You have a physics one next Friday. So how would you feel about a differential equations test next Thursday?
Great linear algebra. Gives me 40 minutes between economics and differential equations. A whole bunch of crap.
Jesse still has 10 minutes.
Oh yeah.
The reason I would pick Thursday
It's still good for me.
is because we should be able to start early on a Thursday. Nobody should have a class between 10:40 and 11:05. Does anybody have a class between 10:40 and 11:05 on Thursdays?
For the study period,
You have a lab?
differential equations.
She screwed it all up.
Yeah, we have one.
Yeah, we have last week.
Bunch of you have lab on Thursday morning?
What lab you guys have Thursday morning?
Yeah,
Is it?
Tom.
Oh, physics one, right?
Oh, that's right, yeah. Jay's not gonna go easy either. She's
All right,
gonna
well,
mine's first. Do better.
this was such an exciting problem, I decided to do it again.
Why?
A different
Why would
way.
you do that?
A different way, I bet. I bet so too. So that problem is homogeneous, but it's also Bernoulli, I think. Let's see. To be Bernoulli, I can't have a coefficient in front of the y prime, so I'm going to divide everything by 2xy. So that gives me y prime equals, I'm going to write this as 1/2 x y to the negative 1 plus 1 over xy. And then if I move the 1 over xy over, I have y prime minus 1 over xy equals 1/2 x y to the negative 1. And I do believe that fits into the Bernoulli pattern, because Bernoulli you have y prime, you have a p of x y, and then you have a q of x y to another power. So this is another good example of, this is an equation you can solve more than one way. It can be solved as a homogeneous equation. It can be solved as a Bernoulli equation.
What would you suggest?
Well, we already did it as homogeneous. Let's work it out as Bernoulli and decide which way we think is easier.
I think I can make a decision.
You think you can make a decision right now? I think I can too. But we'll do it anyway. All right, so how did Bernoulli go again? We did a substitution first.
V equals y raised to the
Y.
V equals y raised to the 1 minus n. So in that case, V is y raised to the 1 minus negative 1, which is y squared. Which gives us y is the square root of v. And y prime is 1/2 v to the negative 1/2 v prime.
I'm pretty sure I know which one's easier now.
So I make those substitutions. I plug in for y prime over here. I'm going to have 1/2 v to the negative 1/2 v prime minus 1 over x, and then y was v to the 1/2 equals 1/2 x, and then this will be v to the negative 1/2, because I've got v to the 1/2 from here multiplied by my power negative 1, v to the negative 1/2. So what happens with Bernoulli equations after you make that substitution? They become linear. They become linear. Not row yet. We're getting close to row. Before we can row our boat, we've got to multiply everything by 2v to the 1/2. We've got to get rid of this coefficient right here.
Wait,
Go ahead.
I don't understand the 2v to the 1/2 part.
We're gonna get
Well, the 2 cancels the 1/2, correct?
But wait,
why do you get to prime by itself?
Yeah, to be in the linear form, I need v prime, a p of x v, and then just a q of x. So I've got to get rid of this coefficient right here.
okay.
So I multiply by the 2 to cancel the 1/2, the v to the 1/2. Those multiply to be 1. All right, so we have v prime minus 2 over x v, because we add those exponents, 1/2 plus 1/2 is 1, equals x over there, because 2 times 1/2 is 1, the v to the 1/2, the v to the negative 1/2, they multiply to be 1. All right, so we do have now a linear equation. We have v prime, we have a q of x v, and we have we have a v prime, we have a p of x v, and a q of x. It is linear.
So we're in a row.
Now we're ready for rho. Rho is e to the integral negative 2 over x dx. That's e to the negative 2 ln x. Bring the negative 2 in as an exponent. E and ln are inverses.
So when did the X go negative?
X to the negative 2. That's exactly what you get. X to the negative 2. You come back here, you take this equation, and you multiply everything by x to the negative 2. X to the negative 2 v prime minus 2x to the negative 3v, because I already had an x to the negative 1 there, equals x to the negative 1. If I've done everything correctly, the left-hand side should be the derivative of rho, which was x to the negative 2 times v. And you can do a quick product rule there and check that that does work. We integrate both sides. X to the negative 2v equals ln x plus c. Multiply by the x squared. V equals x squared ln x plus cx squared. And then finally, I get rid of the v, going way back up here. V is y squared.
Sorry, I'm confused.
Go ahead.
Why do we want to y squared?
Oh, just because I wanted to get the v all by itself.
What can you divide by? Oh, I'm kidding. No.
I could divide by x to the negative 2. Yes, I could do that also. That's the same as multiplying by x squared. You answered your own question there. Very good. Plug my v back in. V is y squared. Y squared equals x squared ln x plus cx squared. The good news is I got exactly the same answer doing it as a Bernoulli equation as I did when I solved it as a homogeneous equation.
Yeah.
So bad.
The bigger question is, which way was easier?
What do you understand better?
The correct answer is, which way do you understand better? That's right. Personally, I think the homogeneous way was a little bit easier. That's my opinion. If I had a choice between homogeneous and Bernoulli, I would do it homogeneous. That's my choice. Sure, you can have a flashcard. You can even write stuff on it if you want to.
I'm allowed. He's like, why do you guys have cards that filled out? I said, you have a card.
No, it may not be a flashcard that big. That's one of the little, what are they?
8 by
8x11 or
No, 8 by 11 is a full sheet of paper. I'm thinking like 3 by 5, I think they are.
3 by 5 by a couple mil.
You may have a 3 by 5 index card on your test.
How many?
Well, this is 3
One.
Could we have separate index cards for each test? Or do they all have to go on one note card by the end of the year for them?
You are definitely going to want separate note cards for separate tests.
Okay.
So we have cumulative note cards for the final.
The note card you will use for test 2, you won't need the note card from test 1 at all. And then the note card you use for test 3, the note cards from test 1 and 2 really won't help you at all.
What about final?
Yeah, can we use your collection of note cards?
On the final, you will get to use your collection of note cards. Okay? The rule with the note cards is you cannot have complete examples worked out. You can have theorems written down. You can have reminders like homogeneous, y equals vx. You can have little reminders like that. But you cannot have complete examples worked out on your note cards.
Just don't write the answer at the end of it. It's not really complete.
You will be submitting your note card with your test. And if I find things that I deem as inappropriate, you will be penalized. So if you work out 99% of the problem, but stop right here, I'm not going to find that acceptable. Don't push your luck there. Other questions? All right, so let's do another homogeneous problem. I'll just pick another one out of the book here. How about x squared y prime equals xy plus x squared e to the y over x. All right, once again, part of the hardest job on this first test you're going to have is to look at an equation and decide which kind of equation it is. Right now we have separable, linear, Bernoulli, and homogeneous. You have 4 choices at this point.
It's homogeneous.
It is homogeneous because I said let's do another homogeneous equation. That's a good guess.
I actually didn't hear you say that.
Oh, so what tells you it's homogeneous?
You have an x squared.
I have an x squared, that's power 2.
X and y both can add together.
xy, that's a power 2.
Then
X squared, that's a power 2. And,
Anything that you
That's
can
a number.
and that's, in a sense, this one's a number because you've got variable divided by variable, so that's power 0 right there. So in essence, that's a number.
Yeah, I was wondering if that actually counted.
Well, if this just had e to the y, then it would not be homogeneous because this would have some sort of weird power to it. So it's important that it does have the y over x. So this is homogeneous. And I think
Wouldn't 1 over x be a power of 1? No, it's 1.
1 over x would be a power of negative 1. And I do think that this one, because of this e term over here, this is not linear and this is not Bernoulli. And I'm very, very convinced it's not separable. So I think this is homogeneous and that's the only way we can solve it. All right, so homogeneous. Our substitution is y equals vx and y prime equals v plus xv prime. We substitute in. So we're going to have x squared times v plus xv prime equals x times vx plus x squared. Oh, I'm sorry. Yeah, that's right. X squared e to the vx over x. So this is e to the v on the end. That's correct. And I got x squared, I got x squared, I got x squared. I can cancel x squared out of everything. V plus xv prime equals v plus e to the v. Subtract the v on both sides. Go ahead.
What happened to that? Wait a minute. So you divided by x squared on both sides, right?
I divided by x squared.
But wouldn't that leave a 1 over x? Because with that one, there's like 1x there. So
There's x and another x. There's actually 2 of them there.
Oh.
There's x squared right there.
Yeah, then there's
So the x squareds do cancel out.
Alright, that's not
Okay?
That sounds good.
That should always happen. If everything was degree 2 at the beginning, x squared should cancel out everywhere. If x squared doesn't cancel out, you made an algebra mistake somewhere. Go back and find it.
Or it's not.
Or it's not homogeneous. That's the other option. You made a mistake in saying it was homogeneous. All right. I'm just going to rewrite this dv dx equals e to the v. And then I separate my variables. 1 over e to the v dv equals 1 over x dx. Once again, when it's homogeneous, you make that substitution, you do your algebra, it should always be separable. All right, I'll integrate the right-hand side.
Thank you.
ln(x plus c. How do you integrate the left-hand side?
Good question.
Good question, that's why I asked
Let me
it.
think back to Calc 2. What did my Calc 2 teacher say? People from
Why don't you figure it out?
Yeah, this is a lot easier than you think.
That's natural logarithm.
Bring up the e to the v. Bring it up as e to the negative v. What's the antiderivative of e to the negative v? Negative e to the negative v. Yeah, you guys were all making that hard.
You need row what again?
Rho, there's no rho in this problem.
So how did you get
How did I get e to the v? Well, these two x's canceled out right there. And then that x squared canceled with that x squared, so the only thing left was an e to the v. No rho. We use rho for linear equations. This one was homogeneous. Homogeneous becomes separable. So there's no rho in that whole process. All right, so the integral of e to the negative v dv is negative e to the negative v. And all that's left to do is, I could take the ln of both sides, but then I'm going to have ln of an ln. That's kind of ugly. I think all I would do is I would get rid of the v and I would plug back in v is y over x. So I think I would leave my answer as negative e to the negative y over x equals ln x plus c. That's how I would leave my answer. Questions on that one?
So wait, we don't need absolute value, that's
Again,
would we be fine if we just wrote it all the time?
yeah, you'd be fine if you wrote it all the time. Again, I wouldn't penalize you if you didn't. Because the vast majority of the time when you're solving differential equations, x is usually time, so x is usually a positive number. So we don't usually worry about the negatives in differential equations. But technically, x could be a negative number there, I suppose.
Okay.
So we'll throw the absolute values in.
How will we know that that's as far as we have to go with it? Like most of the time, I think like we have to try to get it down to y equals.
Yeah, and I mean, if you want to go nuts,
I mean, I don't want to, but
I can get y equals all by itself if I really want to. But usually on one like this, we wouldn't worry about it. I mean, you could go e to the negative y over x equals negative ln x plus c. Multiply both sides by negative 1. And then you could do an ln. So negative y over x equals ln of negative ln x plus c. But usually we try to avoid nested ln's.
so
and-
one thing's gonna be ugly.
if it looks like it's going to be ugly, leave it. Leave it like that. It's okay.
So long as you plug back into the v.
Yep.
How did you get the E again?
Which e?
On top.
E to the v?
No, keep going up. Why multiply by E?
I didn't multiply by e.
If you go up and,
Here?
no.
You can't see what's in the original.
Am I going up or down?
Oh,
Up here?
no.
Up here. Keep going up.
Yeah, that one right there. Why did you?
Okay. So notice that
No, I thought the original problem was,
the original problem had an e in it.
Oh.
So there's the e in the original problem.
I thought you were just doing the line.
Oh. Started with an e in it, right from the original problem. This was number 8 out of the book, in case you're curious. It started with an e in it. I didn't multiply by an e. It was there. Okay, so that's homogeneous. Homogeneous, my opinion of homogeneous is not terribly difficult, but quite a lot of work. I mean, you got to make the substitutions, then there's a bunch of algebra to do, then you got to integrate. Plenty of spaces to make a mistake. Plenty of opportunities. But I think they're easier than Bernoulli, my opinion. All right. The next kind of equation we have are called linear substitution. These are going to look like this. You might have x plus y, y prime equals 1. This is number 18 out of the book. Is it homogeneous?
No.
No, why not?
Because there's no power nothing on the right side. Well, there is, but there's no
This is degree 1, this is degree 1, but this is degree 0, so it's not homogeneous. All the powers are not the same.
Y prime equals 1 is homogeneous.
y prime equals 1 would be homogeneous. More importantly, it would be separable, but because you could just dy equals dx, so that would be the easy way to solve that one. But it is homogeneous also. All right, so it's not homogeneous. Is it linear? Well, to be linear, it's got to be, you're going to be able to write it as y prime plus p of x y equals q of x. So is it linear?
Gotta use Bernoulli, right? Or no?
Linear substitution.
It's a linear substitution, yeah. But it's not linear, because to get the y prime all by itself, I'm going to have to divide by this x plus y. By the same token, it's not Bernoulli, because Bernoulli would look like that. To get this y prime by itself, I'm going to have to divide by the x plus y. That's not going to help. All right, and it's not separable. So it doesn't fit any of the forms we've done so far. What you should notice, though, is that x plus y, that's a linear factor. So this is kind of the last, not the last one, but this is kind of down on my list of ways to look to solve. I look for separable, I look for linear, I look for homogeneous, I look for Bernoulli. If it's none of those, then I kind of look to see if this works. So what I notice is that this x plus y is linear. So we're going to let that be our v this time. V is going to be x plus y.
So that means like with every linear substitution problem, you have to make it like, so if it was 2x plus 3y, the v would be 2x plus 3y.
Correct. If this was 2x plus 3y in here, then v would be 2x plus 3y.
Okay.
Correct. I'm going to rewrite that slightly. I'm going to rewrite that as y equals v minus x. And then I'm going to take the derivative. Y prime is v prime minus 1. And I'm going to make those substitutions. Instead of x plus y, I'm going to write v. Instead of y prime, I'm going to write v prime minus 1 equals 1. And what should happen when you do that, that new equation should become separable or linear. It depends. There's no way to know right from the beginning. So you got to do a little algebra, simplify things a little bit, and see what you can do. All right, so suggestions on simplifying.
Distribute the v,
Distribute the v,
maybe?
maybe. Okay. V prime minus v equals 1. Good start. Next step. What's that?
All I see is V.
Yeah. V prime minus v. All right, let's.
Right, DVD.
All right, so let's write it as v dv dx minus v equals 1. That might help a little bit.
Separable.
Separable.
Yeah.
Okay, convince me it's separable. Tell me the algebra.
Multiply by dx.
If I multiply by dx, I've got to multiply this one by a dx too, so I'm going to have a v and a dx.
So if you add v across and just divide by v, or just back to where.
Can I divide by v
No, from before.
You can add that.
up here? Yeah, I could have divided by v up here.
Added it then.
All right, well, I'll make the same thing here. Let's add the v over. So v dv dx equals v plus 1. And then I divide by that v, and I am convinced it's separable. dv over dx equals v plus 1 over v. And then I absolutely can separate my variables. I multiply by v, I divide by v plus 1, and I multiply by dx. And that all separates. So I'm going to have v over v plus 1 dv equals dx. So it did become separable after making that appropriate linear substitution. Like I say, separable, sometimes they'll be linear, most times they're going to end up being separable.
Would it be 1 dx?
Okay?
What's the
Okay. All right, so once again, I'll be generous and I'll integrate the right-hand side. X plus c. How do you integrate the left-hand side?
Double
It's something. What's that?
Oh, yeah.
You have two choices. Choice number 1 is do long division. Choice number 2 is use substitution. Either one will work. I'm going to use u substitution this time, I think. I would let u be v plus 1, which means du is dv, and then what am I going to do with this v that's up on top? Solve, and I'm going to write it as u minus 1. So this is going to become the integral of u minus 1 over u du when you do that u substitution.
But didn't you just, like, on the top, v plus 1 minus 1 and split it up, so you have v plus 1, the integral of v plus 1 over v plus 1 plus,
That would be a third correct option. A third correct way to integrate this would have been to take this v right here, add a 1 and subtract a 1, and then split it as v plus 1 over v plus 1 minus 1 over v plus 1, and then integrate. So there's at least 3 ways to do this problem. Wolfram alpha would be a 4th way, but you won't have access to that on your test. So we'll help you do it. All right, so this is 1 minus 1 over u du equals x plus c. This is u minus ln u equals x plus c. But u was v plus 1, so v plus 1 minus ln of v plus 1 equals x plus c. And then v, way back up at the top, v was x plus y. So it looks like our final answer is x plus y plus 1 minus ln of x plus y plus 1 equals x plus c. If I were going to simplify, I suppose I could reduce those x's on both sides. And you like, all right, but I don't think I would go any further than that. I mean, you could work on trying to get the y all by itself, but I don't think it would be very easy.
Where did x came from?
What's that?
Why did you put x in there?
Why did this x?
Yeah.
Because v back here was x plus y. So I substituted this v here, I wrote x plus y. Other questions? Do another one of those or move on? Move on? All right. Exact equations. Exact equations are usually very easy to identify because they're usually written in a complete different form. So notice with the exact equations, they're quite often written with the dx and the dy split. However, just because an equation is written with the dx and the dy split does not guarantee that it is exact. To be exact, what has to happen is when you take the partial derivative of m with respect to y, you have to get the partial derivative of n with respect to x. And then you're guaranteed that it's exact. All right, so let me give you an example of an exact equation. Number 32 out of the book. Number 32 has 4x minus y times dx plus 6y minus x dy equals 0. Okay, so if that problem were given to me on a quiz or a test, I would look at that and I would almost immediately say, that's exact. But before I can say that for sure, I do need to check it. So I need to take the partial of m with respect to y. So what's the partial derivative of m with respect to y? -1. And then I need to take the partial derivative of n with respect to x. So notice you're kind of crossing your derivatives. This has the dx, but you take the partial with dy. This one has dy, you take its partial with dx.
Wait, I'm confused.
Go ahead.
The dm over the dy, so that would be the 4x minus y.
Correct. So I'm taking the derivative of this with y being the variable.
Okay, so it would just be -1.
Right, because 4x, with y being the variable, 4x is a number.
Okay.
The derivative of a number is 0,
Mhm.
and that would be a -1.
Okay, that makes sense.
Right, but again, notice how they kind of cross. The m is the one that goes next to the dx, but when you check the partial derivatives, you take the partial derivative with respect to y. So you have a dx here, but you do a dy. dy here, you do a dx. So that one is exact.
What if it doesn't equal?
What if it doesn't equal? Then it's not exact. And you got to figure out a different way. Maybe it's linear, maybe it's homogeneous, maybe it's different. Separable. Maybe it's Bernoulli. You got to try something else.
Wait,
Yeah.
I got a question.
Go ahead.
If this is separable, you usually, okay, I guess, never mind.
Never mind.
So you see there's a...
No, I'm not done yet. I haven't solved the equation. All I've done at this point is proven that it's exact. Now I'm ready to solve. To solve the equation, I'm going to take the integral of 4x minus y dx. What's the antiderivative of 4x?
You're treating y as a constant.
We are treating y as a constant. That's correct. What's the, because we're taking the integral dx, we are treating y as a constant. What's the antiderivative of 4x? 2x squared. Minus, what's the antiderivative of y? Yx, because we're treating y as a constant here. I'm going to write it as xy. Plus c. But this c isn't just a number c. This c could be a function that has a bunch of y's in it. Right? Because I'm doing its antiderivative with respect to x. So to reverse it, if I do derivative with respect to x, anything that has just a y in it, its derivative would be 0. Okay? Then I do the same thing. I take the antiderivative of 6y minus x dy. So I integrate both pieces. What's the integral of 6y? 3y squared. Minus, what's the antiderivative of x? xy plus, I'm going to use k, different letter. And again, this could have a bunch of x's in it, couldn't it? K of x. All right, so what has to happen? What should happen is you look at these two answers. Wherever you have x's and y's mixed, they should be exactly the same. So notice that here we have a minus xy and we have a minus xy, where the x's and y's should be exactly the same. Here we have a 2x squared. Down here we need a k of x. What's k of x? 2x squared. There's the function that only has x's in it. Here we need a function that only has y's in it. What's the function that only has y's in it? 3y squared. So our answer is the solution to this differential equation is a function of two variables. It's the function that has 2x squared minus xy plus 3y squared plus some number c. And I will use c now because c is just a number as opposed to this function that I used back up here.
We did this in Calc 3 a little bit.
Yeah.
You did this in Calc 3 a little bit. Yes, you did.
Vaguely.
Vaguely remember. So what's the good news about exact equations?
It's exact.
It's exact. That's true.
No, there's still plus C in there.
There's still plus c. What's that?
Not that bad.
Well, you might have to use u substitution depending on the functions here. But in general, exact equations are very, very easy to solve. That's the good news. The whole test should be exact equations. Well, we'll see about that.
No, because he makes some really nasty
Make some really nasty integration problems. Yeah.
Let's do trick stuff.
Oh, good idea. right, so exact equations are good for two things. One, they should be the easiest ones to identify because you almost always have the dy and the dx split. And two, once you identify them as exact, they're usually very easy to solve. Two simple integrations in general. And then you equate your functions. Questions on that?
There should be like 3 sections in one.
Well, you notice we've already spent 2 days on it,
Yeah.
and we're not done.
Yeah.
So we will spend more time tomorrow. So I'm treating it almost like 3 sections because I'm spending 3 days on it.
Can I ask something really quick?
You may ask something really quick.
Alright, so why did it not start with 3y squared and then minus xy? Like, do you always just choose the top one?
Oh no, I can put things in any order I want. I could write this as 3y squared minus xy plus 2x squared plus c. I can switch order.
Okay, that was my
The order you write it in doesn't. This is just kind of the standard. When you write polynomials with mixed variables, usually you start with the highest power of x, and then the x's decrease as you go.
okay.
But if you wrote it this way, I wouldn't care. That would be perfectly correct. Mike.
So since you said we didn't finish the section, what homework questions can we do? Or-
You should be able to do any homework problem between 1 and 41.
Skipping.
Well, whatever's listed on the syllabus, I think it's 1 through 41, every other odd maybe.
53.
Yeah.
Right, so you cannot yet do the 43 through 53. We'll do that tomorrow.
So we can just skip questions.